Okay. So now what you do is, you have LEDs. Then coming this way, you can also go to this and then get started. You can see this here. Get started. Go to learn. Go to learn. I have already shown you. I am showing it once again here. For all those who missed, you can see it once again here. Yesterday's class I have shown you how to connect. So if you get any doubt here, you will be able to see here flip-flops. Just click on the left, you will find different flip-flops. The difference between a latch and a flip-flop, the sub-modules, we are doing today JK flip-flop. So your experiment is JK flip-flop, and as you can see in the JK flip-flop, what you can see are the two inputs J and K. One is clock, okay, and you are able to see the feedback connection from Q bar to this end and Q to this end. This also you are able to see. Then this is a stable state table. When J is 0, K is 0, Qt plus 1 and Qt, it remains the same. J is 0, K is 1, Q is 0 because it is reset. When J is 1, it is set, so Q is 1. When they are both 1, it is known as a toggling state. It goes to its complementary state. So if it was 0, it goes to 1. If it was 1, it goes to 0. So the same thing. Now you can see this circuit here. Already constructed circuit. You can also construct. Okay. Maybe I'll show it as a full screen. Yeah. So now you can see 0, 0. What is the state? Q is 0, Q is 1. This is considered as the initial state. So to this state, suppose I apply again, let us say 1. Say it is taking some time. When the clock transition happens only, it will change. Otherwise, it won't change. So Q is 1 and Q bar is 0. So to this state, this is, suppose this is your existing state or initial state. To this, let us say that you are applying 0. What happens? Even if there is a change in the clock, as you can see, the clock is changing. This remains in the same state as 1, 0, which was the initial condition. That means the information is getting locked. So this is how it is used as a memory element. Next, let's give, this was given 1. So now let's give this as 1. Let's see what happens. See, only when there is a transition of the clock that it is changing. Since J is 0, your Q is 0, your Q bar is 1. Now let me tell you, take you to the other state. What is the other state? 1, 0, 1, 1. So you can see it is toggling 0, 1, 0, 1 alternately. Instead of these switches at the output, suppose you connect LED, you can see the LED is glowing on and off. That also you will be able to see. So here we are using JK flip-flop as a block element. Inside this block element is nothing but your NAND and NOR gates. So yesterday what we have seen RS flip-flop, same way inside this you have flip-flops constructed using either a NOR gate or as NAND gate. So I think this is clear enough. So let's go back. So this is one flip-flop, that is your JK flip-flop. Then let me show you about a T flip-flop. T flip-flop is nothing but an extension of D. As you can see, D also has one input if you remember. This T also has one input. It's like this feedback connection is going JK, basically it is JK. It's coming here, and JK is in turn nothing but RS flip-flop with a little modification of the output being connected as a feedback connection. Clock is common. Now what is it the T that you are giving? You are giving this input common to both this AND gate as well as this AND gate. So that means J is T, K is T. In order to utilize, this is a modified JK flip-flop. So other two combinations of J and K are eliminated. There is no need. because it's just one input that you are doing. So if it is 0, it's like a D flip-flop. If it is 0, you will get it as 0. If it is 1, it will be complemented. Why is it complementing? Because both are receiving 1. When both are receiving 1, J is 1, K is 1. It's a toggle. Therefore, it is going into its complementary state. If it is 0, that means what? There is no change. Both J is 0, K is 0. It's a modified JK. So, when you give this T or D flip-flop or T flip-flop, both are delay and toggle flip-flop. If you give 0, J is 0 and K is 0. That means there is no change of state. When there is no change of state, it means that what is this T and T plus 1? The state of the flip-flop at the Tth second and at T plus 1th second. The difference being 1 second. So if you apply a clock of 1 second delay, in that delay it remains to be in its previous state, whereas in this case it will toggle. That is what it means. So let me show you this circuit here. Yeah, now it's seen full screen. Yes. So now clock is high. If you give 0, it is 0 and 1, it remains in the same state. So what are these? These are your presets. So now let's give 1 and see what happens. Can you say it's toggling? This is toggling. If clock is 0, suppose the clock is 0, then what happens? It is not changing its state. Can you see? This is your clock, this is set terminal, this is reset terminal. The yellow one which is highlighted is a clock. I made this as 0. Once this is 0, when this is 1, you are expected this to toggle. This is expected to toggle. It is not happening because your clock is 0. Okay, and these are set and preset. If you make this as 1, even if you make this 0, it will not change because this is already set to 1. Suppose this is reset, you can't have both same. So suppose this is reset, even if you make this 1, this is not going to affect because it's always reset. I repeat, clock is 0. Any change here is not going to affect this. This is the first condition. Next condition, make this as 1, this as 0. 1 at a time, let us see. This is set to 1. The second yellow button is set button. The third yellow button is reset button. So if you set it to 1, if you give 1, there is no problem. You are getting Q as 1, Q bar as 0. No problem. Suppose I make this as 0. Even then it continues to be in the previous state of Q1 and Q bar 0. It is not going to change because it is preset. It is preset to a condition of 1. Preset to set, right? Similarly, if you set this to 1, that means it is preset to, that means it is reset. Reset condition. Initial condition was reset. So if it is 0, there is no problem. 0 and 1 you are getting. Even if you make this 1, this is not going to change. Let me see if you make this as 1. Clock is 1. 0, 0, 1. Clock is also set to 1, but this information is not being conveyed to the output. So the information is getting blocked. It is inhibited from reaching, the input is inhibited from reaching the output. So that means the information is blocked. So it is used as a memory element because it is reset. Since it is reset, even if you try setting, it won't go there. It's not going. It's always 0 and 1. So that means if you want any information coded, and if you want that information which is coded, used as a security purpose and for intelligence reasons, what they do is they encrypt the information. So this is one kind of encryption. So this is how it is. Let's go back. You can construct this circuit very easily. Then you will be talking about master slave flip-flop. So today we are discussing, yesterday we discussed about SR flip-flop. Today we are discussing about D flip-flop, T flip-flop we have seen. Now this is a JK flip-flop. It can be either constructed using NAND or not. And what you have here, this is nothing but a cascading of two JK flip-flops, as you can see the figure here. One is called the master, the other one is called the slave. This we have already discussed. So now let us see its working and its simulation. So this is set and reset. J and K are called as set and reset. Now what is important is the clock is connected by means of an inverter to the slave. So that means if master is positive edge triggered, slave will be negative edge triggered because of this inversion here. So that means slave copies the action of a master after one clock cycle. That is what it means. So the second flip-flop is called slave and it is driven by the negative clock cycle. So if this is positive, this is negative. So during the positive clock cycle, master flip-flop gives intermediate output. The output is given during the positive cycle. But this output will not be conveyed to slave until another transition comes in. Until a negative transition comes in. Until that time, it remains logged in master only. So slave is copying these actions after one clock period. So if you see the circuit, inside, initially this was shown as a block. So now you are constructing, there is a bubble here, I don't know whether you are able to see. These are NAND gates. The second ones are AND gates. The first ones are AND, A-N-D. These are NAND, N-A-N-D. So this is how you connect it. And this is your feedback connection for a JK flip-flop. This Q is connected to K input and Q bar is connected to J input. So now what is the state table? When clock is 0, we have already seen, whatever be the conditions of J and K, it will remain in the same state. Q n plus 1 or n plus 1th second is same as it was in the nth second. If clock is high only, all these information is affected. So we represent this as don't case. Clock is high, J0, K0, whatever be the state, it remains in the same state. And if J is 0, Q is 0 and automatically Q bar is 1 because these two are complementary to each other. And if J is 1 and K is 0, Q will be 1 and accordingly Q bar will be 0. And as before, J is 1, K is equal to 1 will be a toggle state. Yes? Is any doubts? So far, so good. So therefore, Qn represents the state, Qn plus 1 represents, N refers to the at that particular state. And one more thing is, these are all sequential circuits. So these sequential circuits, the output at any given instant of time, please underline the word instant of time. The output of a flip-flop at any given instant of time depends on its conditions and its state of affairs, the state of the flip-flops in the previous clock cycle. Depending on what it is, depending on whether it is in a set condition or a reset condition or whether the clock is applied or whether it is undergoing transition, depending on all these, your output is going to be changed accordingly. So now let us see the circuit of this. Let me show you as a full screen. This is constructed now using not just as a sequential element. Now it is showing you a big circuit. You can construct this circuit using your circuit simulator. Okay. This is your circuit. I think clear enough. So now what's happening? This is your master. This is your clock. Clock is high. Let me give you J is equal to 0. When J is 0, can you see? Q is 0. Q is 0 and Q bar is 1. I think you are able to see that. Now, to this state, let us make K also 0. When it is 0, it is not changing its state. It is remaining in the same state. Though clock is given, though clock is applied, it remains in the same state. Q is 0, Q bar is 1. To this state, suppose I apply J is equal to 1. Now it is changed. So how fast it is changing depends on the clock frequency. If you give the clock frequency 1 second, you will be able to observe a change in the immediate second. If you give a clock of 2 seconds, that means the delay is going to be after 2 seconds. So for an input to be reflected to the output, the time it takes depends on the clock that you are giving. So 1, 0 is over. Now let me make this as 0. So it is remaining in the same state. Let me make this as 1. See, immediately it is changing. That means that difference, but there is a difference as you can see. That difference is dependent on the clock frequency. Now I am giving 1. See, that difference 1, 1. So it is toggling. I think you are able to see the toggling. If you cannot tell it is, you will be able to see this toggling. So this is how you are connecting and you are working out as flip-flops. You can also construct them using the circuit shape oscillator. Okay. My screen is a little low. Okay. So this is how you will be constructing this. Now let me show you how to do using these circuits, how to construct a counter. D flip-flops are over. A race around condition. This also I would like to show you. What is this race around condition? What was a race around condition that we discussed? A race around condition is a condition in which using an RS flip-flop, if R is equal to 0, S is equal to 0. In the case of flip-flop using NOR gates, if R is 0, S is 0, then both Q and Q bar will be in the 0 state, which is forbidden. And similarly, if you construct RS flip-flop using NAND gates, then S bar is equal to 1, R bar is equal to 1 will make Q and Q bar both 1, which you have seen in the last class. So that is again forbidden. That means it is racing, Q and Q bar are racing against each other, which is a forbidden state, and therefore this is referred to as your, what is this condition known as? A race around condition. So before getting into the race condition, what is the JK flip-flop? You have already seen, same as the previous, 0, 1, opposite of the previous, and it is toggling. So now how do we see this? So look at the timing diagrams. This is a clock that you are giving. This is a transition from 1 to 0. This is a transition from 0 to 1. And how much time period you are having here? The total time period is 1 to 0. This is the total time period. But for which period it is off is 0. Half the period it is half of the period. T by 2 seconds it is off and T by 2 seconds it is on. Suppose you are giving J here, K like this. What will be the state of affairs? Let us see. If J is 0, this is a transition, negative transition. Say that it is a negative transition, that means a negative edge triggered flip-flop. So J is this, K is this. So during this part, look at the point where I kept my cursor. J is going high, but K is 0. At this stage, J is high, K is 0. But what is happening at this stage? The transition has gone already. When will it change? Only after a delay of this time t period t that it goes high. How much delay? It is going high, and then at this stage, at the negative transition, this is going low, this is going high. So what is expected when this is J is going low? You expect immediately at this stage, see where my cursor is, at this stage immediately, since K is high, J is 0, you expect Q to be going 0. But it is not going 0 at this stage, it is going 0 at this point. This is the delay. Once again, J is high, this is low, it is low up to here. But it should have gone high at this stage. At this stage when J is 1, see where my cursor is, at this point during the negative transition, J is high, K is 0, we expect Q to go high, but it is not going high here. Instead, it is going high at this point. There is a delay. So these are your delays. Because of this delay, you have a race around condition. T is the time period of the clock, whereas delta T is the propagation delay. T refers to the time period. The small delta T, when you represent a small quantity, generally we represent it by using a very small time period. So such conditions, what you can do is, for such conditions, the time period is considered to be very small. Small delta T tending almost up to 0. So when you do that, during that condition, this is what was expected, but the output may not be same as always the same. So this is called as a race around condition. So now let us look at this. When race around condition is considered. In the previous case, race around condition was not considered, so there was a delay. So when you have a J flip-flop like this and a K flip-flop like this, what's happening? This is the time period during which it is going low. J is high, K is 0. So you expect J to be high here, but there is a delay. Isn't it? Similarly, J is going 0, K is going high. K is going high immediately. K is high, so that means you expect it to go to 0, but it is not happening. It continues to be high. Until what? Until the next transition comes. It will follow transitions now. First transition, J is, here there is a delay. So first time the delay is encountered, so leave that, start from here. Because as it is shown here, there is a delay. So that delay is taken care of before you apply the output. So J is high, K is high. When this transition is coming, J is 0. This is not taking, because of this there is a delay. This is a delay, right? So at this point, since J is 0, this is the delay. So J is 0 and K is 1, and hence it is going low. Now once again, this is the delay. So though J is going high, this is not going high. Where will it go high? It is remaining high. So we expect the entire thing going to be high, but small intervals of time, it is still going low. So J and K are all equal to 1. So toggling should take place. You have taken J is 1, K is 1. And you see, J is 1, K is 1. So 1, 0, 1, 0, 1, 0, 1, 0. This time period refers to this, during which it is 0. So propagation delay has also been reduced. Can you see? It's toggling. So whenever clock is equal to 1, there are consecutive toggling. Whenever clock is high, there is a continuous toggling. Clock is high, continuous toggling. When the clock is low, then it is completely low. This is what it means. So to eliminate this, still there is a kind of some delay which is still there. So what are the methods? It cannot be totally eliminated. There are 3 methods to eliminate this race around condition. One is to increase the delay of the flip-flop, then use of edge-triggered flip-flop. See, the difference between edge-triggered and level-triggered is something like this. If it is edge-triggered, it will immediately respond to either a positive transition, positive edge, or a negative edge during negative transition. So what it means is that it will not wait for the entire level to be either high or low. It will immediately respond when it is taken. So delay of the flip-flop, race around condition can be eliminated. So you use edge-triggered flip-flop rather than level-triggered flip-flop. Now increasing the time delay is another case. The propagation delay, which was represented by delta T in the figure, should be made greater than the duration of the clock pulse. Then it can be eliminated. But by increasing this propagation delay, the race around condition may be eliminated, but there is a possibility of the delay. Delay definitely will come. Then use of master-slave flip-flop, the race around condition can be completely eliminated. Right? So this is how we are doing. Then let me show you about these digital counters. You have already seen different digital counters. So this is the logic diagram. Synchronous counters. These are the timing diagrams. Let us see the simulation of the same. It's loading the image, loading the circuit. here you are able to see 2-bit flip-flop. So JK flip-flop A and B. So this B, according to this particular circuit versus simulator, for them the clock which receives first, the flip-flop which receives first is LSB. The flip-flop which receives clock later will be MSB. So this is continuously kept high, and K and J are joined together. These are your enable. Enable should be always 1. If enable is 0, nothing is possible. You can't see anything. They continues to be as 1 and 1. No change of state is taking place. Only when enable is high can you see 0, 0. 1, 0, 1, 0, 1, 2, 0, 1, 2, 3, 0, 0, 1, 2, 3. I think you are able to see this. So this is counting from 0, 1, 2 and 3. If you connect LEDs here, you will be able to see, or you can even construct using a display, a 7-segment display. So this is how you will be constructing a mod 4 counter. If you add one more flip-flop here, it becomes a mod 8 counter. So this is how you will be doing. You can also go to this circuit, launch a simulator. You have seen the interactive way of doing it. Digital counter, let me show you. This is a digital counter. This is a circuit. Digital decade counter. Decade counter will be counting from 0 to 9. Yeah. So now you can see it as a bigger circuit. So this is the least, this is the most significant bit. Okay. Now let us see. All high 0, 7 this is. 1 1 0 1 is 11. 1 1 0 0 12. This is 9. When you see it is changing, it's counting. It will count up to 9. 1 0 1 0 10. So this is how you will be constructing these circuits. Just check what you are using. So like this, you will be constructing these circuits. I just want you people to reflect on what we are using. Reflect on these and then just tell me whether you are making some sense. So with these counters are over. In the next class, I think I will discuss about counters are over. I will discuss about decoders, encoders, multiplexers and demultiplexers. 4 more are left. So you just go through whatever is being discussed today. In the next class, I will be discussing about those other things. In the meantime, whatever you can complete, all those circuits please complete and post it into